Okay, so today we will be going over section 7.1 and we're going to introduce our next topic of graph theory called trees. So, here we're going to go through a fictional example of where trees might come in. The Amazonian cable network, right? So the the Amazonia Telephone Company is contracted to provide telephone cable and internet service to 7 small mining towns. These towns are located deep in the heart of the Amazon jungle, which makes the project particularly difficult and expensive. In this environment, the most practical and environmental friendly option is to create a network of underground fiber optic cable lines connecting the towns. In addition, it makes sense to bury the underground cable lines along already existing roads connecting the towns. How would you maintain and repair the lines otherwise? Here's a weighted graph model describing the situation. The vertices of the graph represent the towns. The edges of the graph represent the existing roads. And the weight of each edge represents the cost in millions of dollars of creating a fiber optic cable connection along the particular road. The problem facing the engineers and planners of the Amazonia Telephone Company is to build a cable network that 1. Utilizes the existing network of roads, 2. Connects all the towns, and 3. Has the least cost. The challenge, of course, is in meeting the last requirement. Language of graphs. So we want to reformulate the 3 requirements of example 7.1 in the language of graphs. The network must be a subgraph of the original graph. In other words, its edges must come from the original graph. The network must span the original graph. In other words, it must include all the vertices of the original graph. The network must be minimal. In other words, the total weight of the network should be as small as possible. The last requirement has an important corollary. A minimal network cannot have any circuits. Why? Imagine that the solid edges in the figure represent an already existing links in a minimal network. Why would you then build the link X and Y and close the circuit? The edge XY would be a redundant link of the network. So we'll get into a few formal definitions. A network is just another name for a connected graph. This terminology is most commonly used when the graph models a real-life situation. When the network has weights associated to the edges, we call it a weighted network. Of particular interest, as we saw in the previous slide, is where you don't have any circuits, right? So because when we're trying to minimize the connectedness, we don't want any circuits. And so a network with no circuits is called a tree. And that's what we're going over in this section today is trees. A spanning tree of a network is a subgraph that connects all the vertices of the network and has no circuits. Among all spanning trees of weighted network, one with least total weight is called the minimum spanning tree, MST, of the network. The 6 graphs on the following slides all have the same set of vertices, A through L. Let's imagine for the purpose of illustration that these vertices represent computer labs at a university and that the edges are Ethernet connections between the pairs of labs. In this figure, there is no network. Remember, a network is a connected graph. This graph is not connected. The graph is disconnected. The graph is now connected and we have a network. However, in this network, there are several circuits. For example, K, H, I, J, K that create redundant connections. In other words, this network is not a tree, right? So we have a network, it's a connected graph, and the network with no circuits is a tree. Here we have a network but no tree. This figure shows a tree that spans, i.e. reaches all the vertices, We now have a network connecting all the labs and without any redundant connections. Here the tree is the network, right? So by coming over here and taking off this edge and taking off this edge and taking off this edge, now we have no circuits, and so then we do have a tree, and then we get this tree right here. This figure shows in red the same tree as in the previous slide, but now highlights the inside of a larger network. In this case, we describe the red tree as a spanning tree of the larger network, right? This figure shows a different spanning tree for the same network as in the previous slide. Okay, so let's get comfortable with some of the definitions that we've just gone over. It's very difficult to just sit here and listen, but if you work through some of these problems on your own and then hit pause on the video, work through some of the problems, go back and go through some of the terminology, then it shouldn't be too bad. So the following is a list of electrical power lines connecting 8 small towns labeled A through H. So we need 8 small towns: A, B, C, D, E, F, G, and H. A power line connecting A and D. So A and D are connected via a power line. A power line connecting B to C. A power line connecting B and E. A power line connecting B and G. A power line connecting C and G. A power line connecting D and F. A power line connecting D and H. And a power line connecting E and G. Now, do the power lines form a network? Explain why or why not. So rather than just by going off the words, but by drawing our little graph, we can see that the graph is connected and therefore forms a network. So graph is connected. These 3 dots, we read therefore network. All a network is a connected graph, right? Very difficult to visualize that from just the words, but by drawing the vertices represent the towns, the edges represent the power lines, and once you do that, you can see that it is connected. You can get from any vertex to any other vertex along a path. We will call the length of the shortest path joining 2 vertices in a network the degree of separation between the 2 vertices. So the degree of separation between the 2 vertices. So the degree is the length of the shortest path. So consider the network shown in figure 721. How many degrees of separation are there between D and A? Great place to pause the video instead of just sitting there and watching. and try and answer this question on your own and see if you can get that. Um, if you have any questions, feel free to email me. I will upload videos with response to your emails when appropriate. I will just email you back if I don't need to illustrate anything. And also, if I happen to make a mistake that I don't catch on my own, and you'd like to make sure that I made a mistake and that you're not misunderstanding, feel free to email me. But so right here it says how many degrees of separation are there between D and A? So we want to get from D to A. And so definitely there is no direct connection between D and A, so the degree is greater than 1. And if we went to E and then F and then A, we would have 3 edges. But the degree is the shortest possible route. And the shortest possible route, it's got to be between 1 and 3. We see we have a 2 right here, right? And so then go from D to C and then from C to A. And so then the degree of separation between D and A is 2. And so when you do your homework, you can copy the graph, you can show me the path, or you don't have to copy the graph, you can just show me the path, right? So the path is from D to C and then from C to A, and that is 2 edges. How many degrees of separation are there between A and L? Again, so L is way over here, A is way over here, and what you can see is no matter what path we take, we have to go through D. And if we have to go through D, then there's the shortest route is from there to there, so that's 2. So now then the question is, what's the quickest way to A? And we already decided 1. I'm sorry, what's the quickest way to D? And so now we have 1, 2, 3, 4. So how many degrees of separation are there between D and between A and L? And so then A to C, and then C to D, and then D to G, and then G to L. 1, 2, 3, 4. Make sure you answer the question. Right, so the degrees of separation is 4. How many degrees of separation are there between B and H? Right? So H is over here. B is over here. Again, regardless, we have to go through D. So the only way to get to H after we go through D is G and D. And so then the question is, what's the quickest way from B to D, right? And so then there are a couple ways from B to D, either from B to C and then from C to D, which is going to take 2. There's no direct route from B to C, and there's no direct, so then it's going to take 2, and we can get there either B, C, and then from C to D, or from B to E, and then from E to D. Either way, it's going to take 2 more to get from B to D, and it's going to take 2 to get from D to H. So again, the degree of separation is 4. Consider once again the network shown in figure 721. We'll find 2 vertices in the network having 5 degrees of separation between them. Okay, so now we want to have 5 degrees of separation, right? So we saw that from B to H was 4, right? So why start all over, right? So if we start here at B, go to C, then go to D, then go to G, then go to H. We already said from B to H was 4, right? And so then we just go one step further. And that's 5. Find 2 vertices. There is no quicker way, right? You might be able to make it just as quick. By going from I to L, from L to G. That's 2, 3, 4, 5. Either way, it's 5, right? Find two vertices in the network having uh, 6 degrees of separation. And so then we already had found 5. So 5 from B to C. And then from C to D. And then from D to G. And then from G to H. And then from H to I. So then, see, if we go here to J, then we'll have 1, 2. Let me get my laser pointer to help you see that. Laser pointer. 1, 2, 3, 4, 5, 6. But what if we went the other way? 1, 2, 3, 4, 5, 6. Right? So either way, or we could have 1, 2, 3. No matter what, we have to take those 3, right? Or some other. It's gonna take 3 to get to here. And then had we gone this way, 4, 5, 6. Had we gone this way, 4, 5, 6. So this is 6 degrees of separation. So consider once, if you can, find two vertices in the network having 7 degrees of separation between them. If you can't, then briefly explain why you think there aren't any. Okay, so we already saw that for 6 we could start here. 1, 2, 3. And then we go 4, 5, 6. We had that one last time. And so then it might seem reasonable to think, well, all we have to do is go to A, and then we're one step away. But you see, that's not going to work because we don't have to use this edge. We could use this edge right here, and that would take us to the same spot, getting to D in two, using only 2 edges, like we did before when we started here, 1, 2, and then the rest of it is fixed. But starting here doesn't add this edge because we could just go 1, 2. And so no matter what vertex you start with, 1, 2, you can get to D using only 2 edges. So you can't get 7 degrees of separation because the most number of edges that you can have to get to D is 2, right? From any edge on the left, I'm sorry, from any vertex on the left, you can get to D in 2 or less, using 2 or less edges. 1, 2, 1, 2, 1, 1, 1, 2. So if you can't, then briefly explain why you think there aren't any. You can get to vertex D with 2 or fewer edges on the left part and 1, 2, 3, 1, sorry, 1, 2, 3, 4, and with 4 or fewer on the right part. And so that then means then that the most most number of edges that you're going to be able to use is 6. Now we're going to want to be able to talk about that, so we're going to give that a name. One way to measure how tight or loose a network is by looking at the largest degree of separation between any pair of vertices in the network. This number is called the diameter of the network, right? So the largest number, the largest degree of separation between any pair of vertices in the network is called the diameter of the network. And so then that means then that the diameter of this network is 6. We saw that A and, or actually B and J were 6, B and J, 1, 2, 3, 4, 5, 6. And so then we couldn't get any bigger than that. So the degree of separation was 6, so the diameter, that's the biggest one, so that's the diameter. As graphs, next we'll spend some time focusing on trees. As graphs go, trees occupy an important niche between disconnected graphs and overconnected graphs. A tree is special by the virtue of the fact that it is barely connected. This means several things. For any two vertices, x and y, of a tree, there is one and only one path joining x to y. If there were two different paths joining x and y, then these two paths would form a circuit, as shown, right? So if there were two ways to get from x to y, then you could just take, then you would have a circuit. But a tree, by definition, has no circuits, right? So there we go. Every edge of a tree is a bridge, right? So another thing that makes a tree special is that every edge is a bridge. Once you remove that edge, your graph becomes disconnected. Suppose that some edge AB is not a bridge. Then without AB, the graph is still connected, so there must be an alternative path from A to B. This would imply that edge AB is part of a circuit, as illustrated. So if this were not a bridge, taking it out, then you'd have some other way to get from A to B, and if that were the case, then you would have a circuit. So every edge is a bridge. Among all networks with n vertices, a tree is the one with the fewest number of edges, right? So that's not entirely obvious, but if there were a network out there that had, no, we'll just leave it at that. Among all networks with n vertices, a tree is the one with the fewest number of edges, and we're going to come up with a formula for the number of edges in just a little bit. Imagine the following connect the dots game. Start with 8 isolated vertices. The object of the game is to create a network connecting the vertices by adding edges one at a time without making a circuit. So we will let M denote the number of edges you have added, and at any point in time in the early stages of the game, the graph is disconnected, right? So we will let M denote the number of edges you added at any point in time. So we're adding edges one at a time. We're trying to connect this and see what's the least number of edges we can add to make this connected. In the early stages of the game, the graph is disconnected. So here we only added this edge, right? Still not connected. We have lots of vertices we can't get to. So then we add this edge. Still not connected. So then we add this edge, right? And then that's still not connected. So then we add a couple more edges. We've added 6 edges, right? Still not connected because D is not connected. But then finally, we connect E and D, and that gives us this picture right here. And so now we're connected. This picture here is somebody else's attempt, and they only did it with, they needed 7 edges as well. This picture here, same thing, and they still needed 7 edges to get this thing connected. Interestingly, this is as good as it will get. When m equals 8, the graph will have a circuit. It just can't be avoided, right? So that's not entirely obvious, but once you have 8 vertices, 8 edges, when you have 8 vertices, then you're going to have a circuit, right? So this brings us to one of the 3 key properties of trees, right? Property 1, in a tree, there is one and only one path joining any 2 vertices, right? And so the converse of that is, if there is one and only one path joining any 2 vertices of a graph, then the graph must be a tree. In a tree, every edge is a bridge, and then if every edge of a graph is a bridge, then the graph must be a tree. A tree with n minus 1 vertices has n minus 1 edges, right? We saw that with 8 vertices, we have 7 edges, and it turns out that's going to be the case all the time. A tree with n vertices has n minus 1 edges. If a network has n vertices and n minus 1 edges, then it must be a tree, right? So if a network has n vertices and you only have n minus 1 edges, a network means that it's connected, and if you did it with 1 less than the number of vertices, you must have a tree. Okay? Notice that a disconnected graph, i.e. not a network, can have n vertices and n minus 1 edges as shown. But this is not a network. Okay. So property 4, reformulate property 3 to property 4. If a network has n vertices and m edges, then m is greater than or equal to n minus 1. So if you have a network, then you're a connected graph, right? And if you count the number of edges, if you're connected, you have to have more edges than n minus 1. For convenience, we will refer to the difference r equals m minus n minus 1 as the redundancy of the network, right? So the redundancy is keeping track of how many extra edges you have to be connected. If m equals n minus 1, the network is a tree. If m is greater than n minus 1, the network has circuits and is not a tree, right? So the redundancy helps us keep track of what are trees and what are not trees. Okay, so lots of definitions to get used to. So one way of getting used to these definitions is to go through some homework, rereading the definitions, making sure they make sense. So here we go. In exercises 11 through 24, you are given information about a network. Choose one of the following 3 options. A, the network is definitely a tree. B, the network is definitely not a tree. C, the network may or may not be a tree. More information is needed. Accompany your answer with a brief explanation for your choice. The network has 23 vertices and no bridges. Okay, so what we saw earlier, in a tree, every edge is a bridge, right? So in a tree, every edge is a bridge. So if you have a network that has no bridges, then it must not be a tree. The network, so that would be B. The network is definitely not a tree. Accompany your answer with a brief explanation. In a tree, every edge is a bridge. No bridges means not a tree. Okay. So again, what will be most beneficial is if you pause the video and try these on your own and see what I say. And if I made a mistake, apologize, email me. I'll look back at it and we'll I'll respond to you either in an email or a video. The network has 23 vertices and 22 bridges, right? So the network has 23 vertices and 22 bridges. Okay, so if you have 22 bridges and 23 vertices, then every edge must be a bridge, right? And so since every edge is a bridge, then your network is a tree. So A, the network is definitely a tree. Because every edge is a bridge. Okay. So the network has redundancy R equals 0. So redundancy R equals 0. Redundancy is over here. So the redundancy is the difference between m, the number of edges, and n minus 1. And so then if that is 0, that means that m is equal to n minus 1. So R equals 0 implies m is equal to n minus 1. Therefore, tree. Okay, so if the number of edges is n minus 1, then you have a tree. The network has 10 vertices, A through J, and there are 2 paths connecting C and D, right? So if there are 2 paths connecting C and D, then you have a circuit. So it's not a tree. 2 paths connecting C and D implies network has circuit. Therefore, not a tree. Okay. The network has 5 vertices, no loops, and no multiple edges, and every vertex has degree 2, right? So, so the degree of every vertex is even. And so earlier we saw that if the degrees of all your vertices was even, you had an Euler circuit. And if you have an Euler circuit, then you have a circuit. And so then if you have a circuit, it's not a tree. So all degrees even implies Euler circuit therefore not a tree. The network has 5 vertices, no loops, and no multiple edges, and has 2 vertices of degree 1 and 3 vertices of degree 2. So we only have 5 vertices, so let's call the one of the ones with degree 1A. Then it's going to connect to something over here, and we'll call that B. Then if B has degree 1, then the graph would not be connected. So B cannot have degree 1 because then these would be our 2 vertices with degree 1, and they would have no connection to the others. So B cannot have degree 1. So B has to have degree 2, and so it has to be connected to some other vertex. Let's call that C. Again, if C has degree 1, then we would not be able to connect to D and E because it has degree 1. So because it has degree 2, it has to be connected to one of these. And we'll say it's connected to D. And then finally, D has degree 1. If that one is the one with degree 1, then this one we would not be able to connect there. And so it just has to be connected, right? So it has to be a tree. And there's your homework for this section, section 7.1, 1 through 23 odd. I will send you an email regarding your homework and how it's going to be collected and all of that later today. I will upload more videos on Wednesday, and this will take place of you attending lecture. Thank you very much. Have a good day. Stay safe.